Up until now, floating point numbers have been ignored. Floating point numbers are very different. They're stored in a specific format and have their own set of opcodes and even their own set of registers. The floating point numbers are stored, like integers, as base 2 numbers. The number part, the exponent, everything is in base 2. The important thing that you need to remember about this is the fact that many fractional values that can be easily represented as base 10 decimal numbers cannot be represented as base 2 numbers. Just as 1/3 cannot be represented exactly as a decimal number, some values cannot be represented as a binary number. For example, take the number 29.85. The whole number, the part to the left of the decimal, is easy. The value 29 is 11101. The period in a base 10 number is a decimal point, while the binary number, it's a binary point. The bits to the right of the binary point in this case are continuous. The 4-digit sequence 0110 repeats indefinitely. The point is that some numbers that you have an exact value for can only be approximated by floating point numbers. And even if your numbers are all exact, it doesn't matter because intermediate values during calculations will still let the approximations creep in. So just expect your floating point values to be close but not dead on exactly right. The IEEE has defined two floating point number formats used by the assembler. The single precision format contains floating point numbers in 32 bits. The leading bit is the sign bit. It's set to 0 to indicate a positive number and 1 for negative. The rest of the number is not affected in any way by the sign. The exponent is 8 bits. It's stored as an unsigned number in the range 0 to 255. The stored value is biased by 127. To find out what the actual exponent value is, subtract 127. That way, the value in the exponent is in the range minus 127 to plus 128. Remember, this is all base 2, not base 10. That is, the exponent is a power of 2. The 23 bits on the right is the number itself. It's a positive binary number, and it is normalized. That is, every binary number except 0 begins, of course, with a 1 bit at some position in the number. With the exponent being a power of 2, you can slide this base number back and forth by simply adding and subtracting to the exponent. The values then remain the same. Shifting the number as far as possible to the left provides the maximum number of bits for digits. Now, the first bit of every such number is always 1, so the number is actually shifted one more position, and the leftmost bit, the most significant bit, is assumed. It's assumed to be 1. The result is that a normalized number is 24 bits long, with the first bit assumed. Converting the maximum possible value to base 10 shows that this representation has 7 digits of accuracy. The double precision format is made from the same layout, but it takes 64 bits instead of 32. The exponent is 11 bits long, which means it can hold larger and smaller numbers, and it has more accuracy. The first bit is the sign bit, the same as the single precision number. The exponent is 11 bits, which means it can hold values from 0 to 2048. The stored value is biased. To find out what the actual exponent value is, subtract 1023. That way, the value of the exponent is in the range minus 1023 to plus 1024. The 52 bits on the right are the number itself. It's also shifted to the left to a normalized position, which gives the number 15 digits of accuracy. This longer form is the more common form. It's the default format of floating point numbers in C, and it is the form that you'll most often encounter. But there is a longer format that's used by the hardware of the computer. All internal floating point calculations use this extended form. The overall format is 80 bits, which means it can hold even larger and smaller numbers, and it has more accuracy. The first bit is the sign bit, the same as in the other two formats. The exponent is 15 bits, which means it can hold values from minus 16,000 to plus 16,000. The 63 bits on the right are the number itself. That one bit between the exponent and the base has to do with marking and detecting unsupported number formats. This internal format is one that you won't need to deal with unless you are doing some very special things with floating point numbers. Conversions to and from this internal format is automatic.